Begin. So we are in 4.6. We're talking about how to change bases. Let's summarize what we've discovered so far. So let V be a vector space. N-dimensional. Let B and B prime be bases. Let's call them B. W. Bases, then we can create a transition matrix P from, say, B to B prime by so V is a vector space, its dimension is n. What does it mean for its dimension to be n?
The number of vectors in its bases.
The number of vectors in any bases, right? So there must be n vectors in here and n vectors in there. Every basis of a vector space with dimension n must have n vectors in that basis. So all bases will be of the same size, and in this case it is n, because if they have greater than n, they won't be independent. If they have less than n, they won't span, essentially. So if we have two separate bases for this guy, then we can create something that's called a transition matrix. This is the typical notation for the transition matrix, where you put a little subscript that tells you what basis you want to go from, what basis you want to go to. It's to transition from talking about things in terms of one language to the other, or in terms of one coordinate system to the other. And we could figure this out by solving a certain augmented matrix. Okay. So we put the old basis over here, we put the new basis that we want to head to over here. This amounts to pretty much lining them up in order. There would be some ordered basis. So you put, as the column vectors here, you literally list the vectors of the old basis, which in this case is going to be our B. This is V1, V2, all the way up to Vn. And you put those guys as columns. And then over here you put the new basis, W1, W2, all the way down to Wn as columns. Then if you find the reducer or echelon form, because this is a basis, all vectors are linearly independent, they will reduce to the identity. So you'll end up with In here, because it's an n-dimensional vector space. And on this side, you'll end up with the transition matrix, P of B, B prime. And P of B to B prime is the matrix such that if you take that guy and you multiply it by any vector that is written in terms of the coordinates with respect to the basis B, the output will be that vector with respect to the coordinates b prime. So you can change coordinates from one coordinate system to another by multiplication via a matrix, by the transition matrix that switches from one to the other. Now, of course, if one of these is the standard basis, things are a bit easier, but not every time do you want to take the trouble of going through the standard basis and back. You'd have to be doing things twice as opposed to once. So a lot of times it's just easier to just do this guy, and we can translate from one to the other. Specifically, say, if our vector space is our n and our, let's say B is the standard basis, B1, B2, Bn, and B prime is any other basis, W1, W2, Wn. Then, right, if one of the bases you happen to be worrying about is the standard basis, then some things follow immediately from this guy, because the standard basis in Rn, when you put them in as the columns of a matrix, they already form the identity, so you literally don't have to do anything. Then the transition matrix that goes from B prime to the standard will literally just be just the columns of this guy. Right? And you don't really have to do anything. And the reason, of course, being is that setting up old basis with the new basis. If the new basis is the standard, this guy is the identity from the beginning. And so you literally have to do nothing, right? So you literally just, if you want to go from some random basis to the standard, the transition matrix will literally be the columns, just take the columns being those basis vectors. To go the other way, to go from the standard to the other way, what you can do is just take this guy and take his inverse. And this is okay. And by the way, this is in general. Since transition matrices are always invertible. Why? One, we know that because we have to have the same number of vectors that live in the same set, you'll always have something that's equivalent to n vectors with n coordinates. You'll always get a square matrix upon construction. And secondly, because they're independent, the reducer or echelon form will be the identity, which the equivalence theorem tells us that if the reducer or echelon form of something is the identity, its determinant is non-zero. Determinant is non-zero means it's invertible. So a transition matrix will always be invertible. And so in general, we can always find an inverse, and the inverse would of course go back to where we're coming from. So if you want to find P of B prime to B, it's always going to be the same as B to B prime, and then you take the inverse. And P of B to B prime, B prime to B inverse. So those relationships will always hold for any transition matrix. So in the case that one of your bases is standard, it's usually very easy. in one direction, you literally don't have to do anything at all. And to go in the other direction, you just take the inverse of that guy. Right? In general, if you do have to do some work to find this guy with row operations, then to find the guy going in the opposite way, you don't have to do that again. You could just find the inverse of the guy you already found. So that's very useful. And this allows us to make translations, to translate from one coordinate system to the other, which may or may not.
So a transition matrix always exists, is that the case?
Yes.
Also,
So if you have a vector space that has more than one basis, then you'll always be able to transition from one to the other.
also, if you have a basis,
Assuming it's finite dimensional.
a basis somehow structured, like let's say in polar coordinates, where each coordinate is kind of defined with like a function of cosine or sines, would this sort of like, would these row operations kind of work?
Polar coordinates is weird. You have to be careful of how you set that up, because the theta has a lot of equivalence classes, you could say. So you have to be careful how you set that up. But yeah, in general, what you would do is you can translate it to Rn, which I'm going to do some examples of how you can see this with some other functions today. But that is really a general thing. So in the case that you're looking at something weird, like you're looking at angles or functions or whatever, you'll always be able to translate to some case in Rn once you're a real vector space, and you can just do it there. So it comes down to, if you have like a set of radii and a set of angles, then basically what you're going to want to do is look at the set of all linear combinations of those, and that will give you the set of all points in the plane. And then you just take their coefficients and put those into vectors, and now you have things that live in R2. And then you can use this to construct 2 by 2 matrices. So learning a lot about matrices and Rn, it's helpful even in broader contexts, because there are many contexts in which we can reduce the problem to this case. But it's really in chapter 8 when I've been saying that for a long time, but it's just me telling you where we're going. It's in chapter 8 where you kind of see this all coming together. But so far we have we know what a basis is. We are assuming that every vector space will have some bases, and if we have several bases, we can switch from one to the other via matrix multiplication in this way. If our set looks weird, it doesn't look like Rn, we'll be able to translate it to Rn via the coordinates of the basis vectors, and then we can manipulate it that way. Now, we already did one example here. We'll do a couple more and then move on to another section. So you'll see here, we'll apply this in a case where the things don't begin in Rn, but we'll actually still be able to solve the problem via this method. Here's the example. So the vector space under consideration here is P1, this is a set of polynomials of degree 1 or less. Here's a basis for P1, which I call P1 and P2, and B prime, which I will call Q1 and Q2 are bases where I'll tell you what my P1 and P2 are, my Q1 and Q2 are. So P1 is this polynomial, 6 plus 3x. P2 is 10 plus 2x. Q1 is the 2, this guy's 3 plus 2x. So these are bases, so it means that what I'm saying is these two guys are linearly independent, and at the same time, any polynomial in P1, I can express as a linear combination of these two. The same holds for these two guys here. So let us, okay, so here are some things we're going to find. A. Find a transition matrix from B prime to B. B. Find a transition matrix from B to B prime. C. Let this polynomial be minus 4 plus x, and I want you to find its coordinates with respect to B.
So my brother was really late. Oh shit, like, he didn't see how like close that was.
Use a transition matrix
So that's left.
Yeah.
And once
to
it's
find
forward, you can see it was forward.
P with respect to B prime. P. Check your answer to B directly. So here you have guys that they don't live in Rn, they live in Pn, P1 for n equals 1 in particular. So it's P1 over R. So we're thinking of R as where the scalars live. Turns out that these two guys are linear independent and span. Same thing for these two guys. I want to be able to now talk about this set in terms of matrices, finding a transition matrix. So first here, the step one is to actually do this translation. Using S equals 1 comma x. This is the standard basis. We can write P1 as coordinates. In fact, we can write all of these guys as coordinates. So P1 is going to be 6, 3, P2 will be 10, 2, Q1 would be 2, 0, and Q2 would be 3, 2. So the fact that just of how a vector space is set up, we can describe things in terms of linear combinations, and once we can get linear combinations, we can just use the scalars in front to create coordinates. And so something might not be a coordinate itself, but I can think of it as being equivalent to a coordinate. And once I'm here, now these things, I can think of P1 as somehow being connected to some vector in R2. And so now what worked in R2 is going to work here. So now let's solve this problem. How do we find A?
You gotta set up the thing.
Set up the thing. Set up the thing. Okay. So what? How does the thing?
The new thing on the left.
Right. You want the new basis over here. You want the old basis over here. So I want to go from B prime to B. So B prime is my old basis, which means that's the Q1 and the Q2. So the old goes on the right. I'm just going to list these in order. That's Q1. This is my Q2. And then I want to end up in the P1 universe. So 6, 3, and 10, 2. Now I'm going to find the reducer echelon form of that. And now this side is going to give me the identity. I believe I pre-computed. So this is like that cooking show. We mix all the ingredients and put it in the oven. Bing! no, yeah. Wait 3.5 hours and then this comes out. Like, no, you did something. There's some sort of magic happening there. Yeah. So you do your bing, and it gets here. Yeah, those cooking shows, man. Like, it looked just like you before I put it in the oven. It doesn't look like that when it comes out. So something happened.
Just a quick statement, but I could also just take the inverse of the old and multiply it by the new. That would be equivalent, right? If I found the inverse of the old one and then applied that to the new one, do the same transition matrix.
You mean take the inverse of this
Yes.
and do what?
And then multiply it with the new, or new times that inverse.
I don't think so. Because what are you saying to do that? You're saying that if I look at the matrix for B, if I multiply that by B prime inverse, that somehow gives me the P?
Yeah. No, sorry, B times B prime, yeah.
Seems too elegant.
So you're saying B would be the transition from
Talk about it because it's just something.
B prime to B times this guy. I think, would that actually work? I'd have to like do computations here. I don't know, I've never done everything all at once like that, but, because it's the rows of this times the columns of that. I don't know, I'd have to write it out. I doubt it though, I feel like something would break. But we can verify this.
We can talk about it after.
You can verify, it's a 2x2, so it shouldn't be that big of a deal.
Wait, are you trying to use that other one that he just wrote?
What?
The other one?
What other one?
Well, that thing, P, the transition matrix from B prime to B is equal to like, the transition matrix of B to B.
We know that this is true. For a single vector in terms of this coordinate, then I can get that vector in terms of this coordinate. If it happens on scale with a bunch of vectors all at once, arranged in the columns of a matrix, I'm not sure. So we can check that. For now, let's go with this.
Okay.
We know this way works. We would have to look into that. Or maybe Young can look into it, he likes investigating. He'll come back with me today with a long email. This I don't think you know. Yeah, so in this case, this means at the end of the day, our matrix to transition from B prime to B will be this 2x2 matrix. Well, one thing is for sure, the dimensions work out, because this will be a 2x2 times a 2x2. You get a 2x2. I don't know if you get that specific 2x2. And so that's our PB. Now, for B, we can do this again, except just swap these two. So we have options here, or I can just realize that this is PB to B and take the inverse of that. So this will actually be the inverse of this which is going to be bing. Let me take it out of it. That's what that's going to be. Or you could set up this guy, but in the opposite way, 2, 3, 0, 2, 6, 10, 3, 2. You do your reducer echelon form, you'll end up with I2 here, and on this side you'd end up with that matrix. Let's leave this there. So that's your A and B. So this is a vector. How do I find its coordinates in terms of the basis B? So P is equal to minus 4 plus x. This I'll think of as equivalent to minus 4 comma 1. I need to find that guy's coordinates in terms of the basis B.
You augment with B and that.
Right? So this implies we need to solve for the basis B. What was the basis B? 6, 3. 10, 2. Minus 4, 1. Right. You could also take the inverse of this times that based on the what I told you about changing from the standard basis, because this here is in the standard basis. But if we do that, we would simply get one minus 1. This means P of B is the vector 1 minus 1. And you can check that. Let's make sure that actually makes sense. If I look at minus 4, 1, I claim that that is 1 times the first basis vector plus minus 1 times the second basis vector. Is that the case? Well, yes, 6 minus 10 is minus 4. 3 minus 2 is 1. So that actually works out. Let's find the coordinates in terms of the other vector, but here they're forcing us to use a transition matrix. So how would we do that? We know that P of B prime is equal to, how would I use a transition matrix to figure that out?
Multiply P of B by P of B to B prime.
Right. So I start with P of B, which we just found, and then I'm going to transition it from B to B prime. So I'll multiply by that transition matrix, which we found in part B. So that was 1/18 times
-4, 14.
I think I miscopied something. See, it's just like in those cooking shows.
Kill a bird.
This is actually supposed to be that, so recopy.
On the old one too?
This one.
Oh,
here.
okay, just on that.
B to B prime, so part B, this was the answer. It's not that 1/18. The 1/18 thing was actually just a simplification of that. It was just right underneath. So I'll take this multiplied by this coordinate, in terms of B, so it's 1 minus 1. And what we end up with is something with fractions, minus 11 over 4 and a half. So P of B prime is that vector. And the fractions might scare you, so all you have to do is to convince yourself is to do that check. Is it true that minus 4, 1 is going to be minus 11 over 4 times the first basis vector in Q plus 1/2 times the second vector in Q, which are the vectors 2, 0, and 3, 2. So this would be minus 11 over 2 plus 3 over 2. That gives you what? Minus 8 over 2, which is minus 4. This would give us 0, 1/2 plus 2 is 1, so that actually works. Oh, and this was part E. Check your answer by doing it through. Although you might go the long way around. So for E, you might, to check doing it directly, you might just actually set up this guy minus 4, 1 with 2, 0, 3, 2, and if you reduce that, you should get 1, 0, 0, 1 times minus 11 over 4, comma 1 over 2. Here's an important takeaway of this section. In the conceptual kind of case, switching from one coordinate system to another involves manipulation of the bases. So this is the idea that I can sort of change the entire way I'm looking at the world by only manipulating a few things, right? So if I manipulate a few things, so I can look at the vector space Rn. If I just take n vectors out of Rn, so Rn contains an infinite number of vectors, but I can take n of them, just a finite number of vectors, and somehow figuring out, tweaking those, I can really rearrange the entire space itself. I can take any vector in one way of looking at bases, multiply by a certain matrix that really came from me manipulating basis vectors, and then the entire universe can change to another way. I can switch from one coordinate system to another by just manipulating and playing around with a finite number of vectors. In other words, we can, probably not the right word to use here, but I want to be more intuitive. We can rearrange a space by just manipulating basis vectors. So the idea comes down to, if you're worried about, there are situations that I mentioned, like the rotation of axes kind of thing, where you might have this thing here, which visually you can tell it's an ellipse, but a computer might not be able to tell. How do you actually do this translation? Because to convert from this to that, technically what you're doing is you're taking an infinite number of points that are around this guy and just remapping them to different locations in the same space. But the thing is, how can you actually do that? How can you manipulate an infinite number of points and change them all? The idea is you don't have to do that. Literally all you have to do is look at the basis vectors in the space that you're talking about, like in R2, I and J might be basis vectors, and just manipulate those guys. Move this guy to here and move that guy to there so that when you tilt your head, it looks like this, right? So I don't have to worry about doing an infinite number of operations. I only need to worry about 2 operations. Change the basis vectors and literally the universe will rotate to accommodate us. That's a very important takeaway that you can get from this idea. So changing the bases will trickle down to literally everyone. Everyone can obey the bases by you just multiplying by some particular matrix that does the translation. And so this kind of leads to 4.9. We're skipping a couple sections, but I think it's nicer to deal with this right now. Where we're talking about transformations in the plane. I'm not going to talk about all of them or show all of them, but I'm going to show a few examples where this idea really explains that entire section. So we look at R2 and R3 because those are the ones that are easy to visualize. And of course, these are called linear transformations. And we are taking the geometrical view. Linear transformations, they are matrices, and we know that ultimately, but geometrically, what a linear transformation is, what are some linear transformations? Give me some examples. If you know of any.
Rotation.
Rotation is one of them. Right? So the idea of taking some vector and rotating about the origin, that gives you a linear transformation. You need the origin in the mix because you need it to be a vector space. So rotation, things like reflection, things like projections, things like compression or dilation, things like expansion and contraction, things like shear. I believe that's all of them. Might be missing one or two, but that's all the linear transformation. So the idea, if you're playing around with 2x2 matrices and you're doing a change of basis, and you're multiplying this 2x2 matrix by some 2-dimensional vector, it turns out geometrically what is happening in a pictorial sense is going to be one of these. Like multiplication by a matrix will result geometrically in one of these things. If you're doing something else in a plane that cannot fall into any one of these categories, you cannot obtain that by multiplication of a matrix. That we'll justify later, but for now, I want to explain to you where some of these matrices come from. So there are standard matrices that we use in R2 to perform some of these, and in 4.9 they'll give you like these huge tables that tells you, okay, you want to rotate by this angle, multiply by this matrix. If you want to project onto the xy, onto the x-axis, multiply by this matrix, right? So now I'm just going to kind of tell you an easy way to figure those matrices out without having to memorize them. And the crux of the matter is, you can figure out these general matrices by just figuring out what happens to the basis vectors. Because I can never remember them anyway. I mean, if I ever need them, I can look them up, but if I was on a desert island and I needed to figure out how to rotate vectors in R2 by an angle theta, I could do it from scratch without any technology. And it's not as hard as you might think, so let's apply the principle. at the end of the last section. To find a matrix in MQ2 so that AX rotates the vector x in R2 by theta counterclockwise. About the origin. Okay, so let's figure out what this guy would have to look like. And I'm sort of going to use this idea of a change of basis, right? So basically, the upshot is going to be, if I can figure out what matrix will do that for the basis vectors, that matrix will do that for every vector. Because every vector, ultimately, I can write as a linear combination of those vectors. And so if I manipulate those vectors, every vector in the space will also be manipulated in exactly the same way. And so that's one way in which basis vectors are extremely useful, and this is also a case of where functions are useful. So you can actually use a function to manipulate the sets that you're working on. Because ultimately matrices will represent functions for us, special kinds of functions. So let's actually look at this, right? So here's my space R2. How would I be able to rotate any vector by an angle theta? Well, let's look at what happens to I. Right, so here's my vector, the I vector. Right? So we have to know, what would A times I do? Right? Let's say I want to rotate counterclockwise by some angle theta. Now the question is, how does this vector change to that vector? What would that vector be? So this is, here is the vector 1, 0. What would this vector be if I were to describe what it is?
Is it like cosine theta, sine theta?
Okay, so yeah, let's create this right triangle. I know that this is the y coordinate. The y coordinate would be?
It would be sine theta.
It would just be sine theta, r sine theta, right? Where my r is 1 in this case. What would my x coordinate be, which is this? That's the adjacent side to theta, so that's going to be my cosine theta. Right? So it turns out my I vector will change to the vector cosine theta, sine theta. Okay, let's move on to the j vector. Right? So let's say I have this vector here. That's the vector 0, 1. I want to rotate that counterclockwise by some angle theta. So the matrix I care about must be the matrix that turns J into something else. And we can do a similar construction here, create a right triangle. The x coordinate here is actually going to be the sine, right? That's going to be the sine of theta, with one difference. It brings me to the negative side. So this would be negative sine theta. This guy here will be the adjacent side to theta, so that's going to be a cosine, and that still gives me a positive number, so this would be cosine theta. This means, here's the matrix that I need. Cosine theta, sine theta, minus sine theta, cosine theta. So I went from 1, going from the standard basis, that's 1, 0, 0, 1. I simply change this first basis vector to that, change the second basis vector to that. Manipulating the basis vectors will give me this matrix that can manipulate any vector. And so this would mean that this guy, cosine theta, sine theta, minus sine theta cosine theta multiplied by any vector x1, x2 rotates this vector by an angle theta. Counterclockwise about origin by theta. And this is a consequence basically of 4.6. I mean, you have to do a little work to prove it, but at this point, I'll just state it and you can believe me. I mean, you can go and prove it yourself, but essentially, we can changing the basis vectors will change ultimately everything, because everyone can be written in terms of these basis vectors. Right? And somehow doing a certain manipulation on my basis vectors, if I throw that into a matrix, multiplying any one, the same manipulation will be done to them. It's kind of an elementary matrix kind of situation going on. Right? So when you go into 4.9 and you'll see something like this in the table, if you're in R2 and you want to rotate things, use this matrix. They'll call this the standard matrix of rotation. Right? And where this came from is this idea. There are other ways to do it using maybe calculus or rotation of axes that you learn from Calc 2, but in terms of linear algebra, this is probably the easiest way to do it. And I think this is probably the easiest way to do it in general. So even if you know other methods, odds are they're going to be more complicated than what we just did. Let's do another example, maybe not so, maybe you guys tell me how to do this one. Reflect over x-axis. Right? In other words, like if I have this vector here, I want to move him to this vector here. So I want to find some sort of transformation that takes any vector and just flips it in the x-axis. This is reflection over the x-axis. Can you tell me a matrix that will do that in R2? How would we figure that out?
We look at what we did to we see how our basis changed.
Okay, so let's look at the I. What would happen to I? Okay, so my I is right here. Okay, reflect over the x-axis. What will happen to that guy?
Nothing.
Literally nothing, right? So my I stays the same, right? Or you can think of it as changing to itself. Here's my J. It goes here. And what would happen to him?
Negative.
He would flip upside down to this guy. Now this vector here was the vector 0, 1. This vector here becomes the vector 0, negative 1. You can think of it as the negative of J, but ultimately what happens is you'll realize that the matrix A that you need to multiply by would be the I, the guy that's usually in position I, will not change at all. The guy that's in position J, we take as negative. And it turns out if you take any vector like that, so here you can even check 1, 0, 0, minus 1, take any random vector x, y, it will give me x minus y, right? So this here is the vector x, y. You'll notice that my x component will remain the same. My y component, however, will become negative, and this is equivalent to reflecting over the x-axis. Once you can make it work for the basis vectors, it will work for everyone. So So you'll also see this in a table. The standard matrix of reflection, they'll tell you, oh, in R2 it's this guy. How did they figure that out? Well, they figured out what it did for I and j. And this manipulation can really work with any basis that you take. It's just that I and j are the easiest ones to do because they're perpendicular to each other and they're in a nice position. You just have to deal with ones and zeros, which is easy to deal with. So this principle you can actually apply in general, but it's nice to apply them to I and j if you want to have a quick answer without too much trouble. Yeah.
So every time we do a row operation, are we doing a linear transformation relative to the previous matrix? Can I think of it?
Yeah. Geometrically, a row operation, well, it depends on what kind of row operation. So a type 1, type 2, type 3 will result in different things. A type 3 is more like a shear.
What's the shape?
So a shear is when, if you have something like the vectors that give you a rectangle, a shear sort of shifts it in one plane. Like you're just taking it, so geometrically speaking, if you look at all the vectors along the edge of this guy or vectors that go to the points here, a type 3 operation will shift them according to some scalar while maintaining in one direction. So that's why it's like this row plus a multiple of another row shifts it in the other way. A type 1 operation is more like a reflection. That's where you get the negative of something. And a type 1 is more like a reflection, and a type 2 is more like a stretch or compress. So they do have geometric interpretations as well. So that's basically all you need to know for 4.9. I gave you a handout for 4.9, it's on the website, you can download it. But what it is it's just a table of all these standard things. So they give you all the linear transformations and they tell you, okay, if you want to do a reflection, use this matrix. If you want to do a rotation, use this. If you want to do a shear, use this. But how they figured it out was by doing this. So I just wanted to show you how to construct such a table so you might not have to remember everything. So linear transformations can have geometrical, well, they do have geometrical interpretations. It's nice to see them in R2 and R3. The same would apply for any dimensions, but of course, in R1 you'll never see it, and in R4 or higher you can't imagine it. So R2 and R3 are usually where we're applying these things. But it'll work in general. Which brings us now to 4.7. Which is a lot of definitions of new terms that will help us with 4.8, which expands the equivalence theorem, which will help us with chapter 8. So in this guy, we're going to talk about things like row space, column space, and null space. So let's look at the definition. So I'll tell you what these are. I'll tell you how to find them. I'll talk a little bit about some consequences and uses, and then we'll see in chapter 8 how they will apply to the equivalence theorem, and we'll get some more mileage out of the equivalence theorem that way. So let's do a definition. Let A n by n be a matrix over R. It's also going to work for C, but we're only really dealing with R. So this is just an n by n matrix with entries that come from the real numbers or the complex numbers. So usually the set R or C is denoted by boldface F. So I can state things in terms of F. To be slightly more general, but not very nice. Then 1. The subspace of Fn spanned by the row vectors of A is called the row space. It's the row space. It also has a notation, row of A. So that expression means the row space. This is just the space spanned by the row vectors of A. Notice that it is a subspace of Rn, so it's a subspace of the number of columns. And we'll see why it's in Fn as opposed to Fm pretty soon. The subspace of Fm spanned by the column vectors is the column space of A. That's COLA. So that represents a space. And because their space is spanned, it means we're talking about all possible linear combinations that you can get from the row vectors or the column vectors. So these guys are subspaces in their own right. They are vector spaces on their own. What else do we want? Well, oh, this guy we already we already defined the null space before, so it's just the solution space to the vectors. For the null space of A. What is the subspace of Fn? The space is row A, column A, null A, and the null of the transpose, which might not be the same. These are very important spaces to study. We call them the fundamental matrix spaces. Knowing a lot about them tells us a lot about our matrix and the sets that its domain and range in general. Space, so given any random matrix, the space spanned by its row vectors is a subspace of Fn. It's called the row space of A. And space spanned by the column vector is the column space of A. The solution space to the homogeneous equation where A is the coefficient matrix is the null space of A. And those spaces together with the null space of A transpose form the fundamental matrix spaces. And they're fundamental for reasons that they help us expand the equivalence theorem, which we're going to talk about in 4.8. But for now, you can know that that's what they're called. Here are some facts. which are going to help us find them actually. Row operations do not affect the row space. In fact, row operations will be very convenient for us to do because it allows us to kill dependent rows. Eventually, if a non-zero row goes to a row of zeros, it's because it was a linear combination of the other rows in the matrix. And actually doing that will not affect, so doing row operations is not going to affect the space span because the most you will do is eliminate rows that are dependent with other rows anyway. By a similar fact, row operations do not affect the null space. Which is, of course, super important. The null space is given by solving a system of equations. We already discussed that doing row operations do not affect systems of equations, the solution space to a system of equations. So it's not going to affect that. The same cannot be said of the column space though. Row operations may affect the column space. The first two facts are probably things that you're already convinced of because we were using these facts to solve systems. So if those two weren't true, we'd be in trouble. The third one though, I can justify it with an example. Take there'll be many examples, but here's one of them. A guy with two identical rows. Then notice I can do a row operation on that. Where this is just row 1 minus row 2. Now let's look at the space. Let's look at the space spanned by the columns. I'm basically going to show you that they're different in this very small case. So in the first case, if I look at the columns, say C1 is 1, 1, C2 is 0, 0, describe the span of that space for me in R2.
The line y equals x.
It's the line y equals x, right? It will be all linear combination of these guys, which is a scalar times this plus a scalar times that. This guy's just 0, so we can ignore that. So the space spanned by this is just scalars of this guy. So that is this space here. It's that line. So the line y equals x is the space span. So it spans a one-dimensional space in R2, and it spans the space that is actually the line y equals x. What is the space spanned by these guys though? So in this case, my new C1 prime is going to be 1, 0, and C2 prime is still going to be 0, 0. What is the space spanned by this guy?
The y
The x-axis?
The x-axis. It's this guy. Which is the line y equals 0. So by doing a row operation on the matrix, if I'm looking at the columns, things can actually change on me. This will never actually change if I look at the rows. So with columns, that stands to reason we can use row operations to help simplify things, to help us find these guys. And in fact, that's what we normally do in this case anyway. But for this guy, we have to be a little bit careful. So for this case, what will happen is, after we do our row operations, we have to take the columns that are corresponding to this space, but we have to take those columns from the original matrix and not this new reduced form. So that being said, let's look at how to find these spaces.
Just a quick question, but what about, can you clarify fact one? Like, the same you did a row operation, and you're saying a row operation is in effect, what is it?
Yeah, well, if I looked at the rows, row 1 is actually 1, 0, and row 2 is actually also 1, 0.
Oh, so it
Here-
still exists, I see.
Row 1 is 1, 0, and row 2 is 0, 0. But the space span by this pair is
Right,
the
it's
same
the
as
same.
space span by
Okay.
that pair. This is a silly example, they look the same, but even if the numbers were different,
You could represent it.
you'd be able to represent these guys as linear combinations of those guys, and it will give you exactly the same space. It's not true for the columns though. Okay, so in light of these facts, we can do the same. So null space we can compute same as always. Actually find the solution to AX equals 0. To find the row space, or you can't really find the row space, you can find a basis for the row space. Because the spaces themselves have an infinite number of things in them potentially. So we're talking about we can find a basis for these guys. We can find a basis for the null space by finding the solution to that. We can find a basis for the row space by finding the row echelon form of A or the reducer echelon form of A. In class I'd find the reducer echelon form so that everyone can get to the same answer. And taking the non-zero rows, or the rows with pivots, if you want to think of it that way. Rows with pivots. And you can take the rows from this reduced form because row operations won't change that guy. For the column space though, we have to always go back to the original guy because our manipulations to simplify things might affect the column space. So basis for the column space is after we do our reducer echelon form to figure out what columns contain pivots, we just take corresponding columns in the original matrix to those columns, and that will give you a basis. Let's do an example. I'll do an example, we'll check for some consequences of that example, and then we'll move on to the next section. And I may not give you a matrix this large, but this is a pretty good test question. So you can expect to be able to be asked something like this. It's considered one of the important ideas in a first semester. And it'll be asked in pretty much exactly the same way. I'll give you a matrix and say, oh, find a basis for all these things. Because the columns can change on us, you can somehow think of these columns as V1, V2, V3, V4, and V5. I'll label the columns of the reduced form by different letters. So if I give you that, what you would need to do is to find the row echelon form or reduced row echelon form, which involves, of course, doing row operations to achieve the form. In this case, the reduced row echelon form of A you put it in the oven and ding, this comes out. It's going to be 1, that would come out. Let's call these columns here W1, W2, W3, W4. Let's do basis for row space. So here you will simply pick the non-zero rows in this reduced form. Notice that the first row, second row, and third row are non-zero rows. The last row is a row of zero, so you ignore them. These three rows will form a basis for the row space. 1, 0, 0, comma, 0, 1, 0, 6, comma, 0, 0, 1, 0, 0. I mean, the space spanned by the row vectors of this matrix is precisely all possible linear combinations of those three vectors. You will notice that these vectors live in R5, right? And R5 is the number of columns here. So you see that how it makes sense with what I said before. Notice that there are 4 rows and 5 columns, right? So this gives us a subspace of R5. Right? The idea being is this guy here, you can think of being equivalent to some function that goes from R5 to R4. So the row space is a subspace of R5. Let's move on to, we also want to find the column space. What is the column space of this guy?
V1, V2, and V3.
Basis for column space of A. Which one?
V1, V2, and V3.
Right. So here we can identify who are the guys we want to pick. I want to actually pick the first 3 columns, but I can't pick them from here because doing row operations could change where the space that they span. So what I want guys that are corresponding to W1, W2, and W3. So I'll take V1, V2, and V3. So this is V1, V2, V3. Or if you want to write them out, which you may want to do, it's actually the column vector 1, 1, minus 2, 1, minus 2, 1, 1, minus 2, 1, 2, 2, minus 1. Notice that this is a subspace of R4. Subset of. So A here is a 4 by 5 matrix. And row space is a subspace of R5, the column space is a subspace of R4, and that's how you'd actually find them. For the null space, you have to go a little bit further and do a little more work. Basis for null space. So here what you would do is you want to solve AX equals 0. We could use this to our advantage, but we still have to do some more. The idea would be to augment and reduce to obtain. What you would obtain is that guy augmented with the 0 at the end. We know this is always consistent. It has, at minimum, the trivial solution. Let's see if it has anything else. As good a time as any to remind ourselves how to solve a system. So if you had this set up here, what would the solutions be? Let's say I define variables for this guy, x1, x2, x3, x4, x5. How do we solve for them?
First, parameterize x5. No, x4 and x5.
So set x4 equals t, x5 equals r, and then move on to row 3. Row 3 would tell us that x3 is actually 0. Move to row 2. So you go from the bottom rows up. Row 2 tells us that x2 minus 3 x4 is 3t plus 6 x5 equals 0. This means x2 would be equal to 3t minus 6r. And go to row 1. x1 is also 0. So this means the solution is 0, x2 is 3t minus 6r, x3 is 0, x4 is t, x5 is r. We can split this into guys who are coefficients of r and t. So this would be 0, minus 6, 0, 0, 1. And I can have coefficients of t 0, 3, 0, 1, 0. And so the basis for the null space are those two vectors. Subspace of R5. So they of course live in your domain space here, because we're talking about the solution space. Think of where the x's come from. That would be the basis for the null space.
Just to clarify, the dimensionality would be 2 though, right? For that basis, or this is
The dimensions of the solution space is 2, so there's a 2-dimensional subspace of R5 that solves this equation.
okay, but it's still in okay.
Right. So the vectors that you can plug into this equation to get 0, they will all live in the plane formed by those two vectors,
Okay.
is what you're saying. Any vector not in that plane will not solve this equation. So there's some uses of these. Like if you had to go through and do this, you can actually get away with some things here. So So what if someone were to ask you in some other context, what is the space spanned by those guys? Turns out that your answer to that question would be the column space of A. And the column space of A had how many vectors?
3, I think?
There were 3. So you know, for example, this is a 3D space. So let's say you had some 4th dimensional vector space that you wanted to find a basis of, and you know that these 5 vectors live in that space. Sure, you know at least one of them have to be redundant by our previous methods. But you want to say, can I take a subset of these guys that will span the entire 4D space? The answer would be no. So it means if you want a basis, you need to find someone else. It's not one of these guys. You need someone who's not represented here to be added to your list, which you can add to them by the plus minus theorem. But we can know that the space spanned by these 5 vectors is actually a 3D space because 2 of them are redundant. So another thing you can know is that only 3 of the vectors v1, v2, v3, v4, v5 are linearly independent. There are 2 dependent ones. Right, so if you went through and you found all these guys, you would be able to know how many of these vectors are linearly independent. And on top of that, you can actually find out the relationship to know who the dependent vector is. Example. It's here you can realize that v4 is actually just -3 times v2, because you can actually look at the vectors and see that relationship holds pretty easily. You can also see that v5, once you reduce it and you put in a lot of zeros, it's easy to see relationships start to form. And you realize that v5 is actually dependent on v2. It's actually some multiple of it. And how you can tell that is because it's easy to see that this relationship holds for the w's. That same relationship will be extractable for the v's. And so even though the v's had a bunch of numbers that were non-zero in it, we can know the relationship between them. So that's a useful way. So you can give me a set of vectors, and if for some reason I need to find how many of them are linearly independent, what dimensional space do they span, I can simply throw them all in a huge matrix, do a reduce or echelon form, and find the column space. Here are a couple other facts. I'll just state them, we won't prove them. But these are things that you can know. Tomorrow we'll move on to 4.8, which is going to be very quick. I don't have much to say from 4.8. So we'll move on to 4.9, which is a fun section. 4.9 is a fun section. That's when we're going to start to take on this linear transformations idea and start to look at things as functions. We're going to start the functional view tomorrow.
Professor?
Yeah.
You mean 4.10?
4.10. 4.9 was the transformations in the plane. So tomorrow we'll do 4.8, which won't take a long time, 10 minutes or so, and we'll move on to 4.10, where we're starting to move into the functional view of things. Think of these as linear transformations. So here are some theorems. AX equals B is consistent if and only if B is in the column space of A. Now we know that this is consistent if and only if the determinant of this guy is non-zero, for example, from the equivalence theorem. But notice that this criteria here would apply even if that guy is not a square matrix and you can't find a determinant and you can't say whether it's invertible or not. This characterization is far more general for knowing when a system will have be consistent. That's one thing. There's another theorem. So let AX equals B be a consistent system. So this is a system where we know there's a solution. And let X naught be any solution to AX equals B. So I know it has at least one solution. Pick a random one. Let this guy V1, V2, Vn be a basis for the null space. So I have a consistent system, give me any random solution, and find a basis for the null space, and here's what we will be able to say. Then every solution to AX equals B can be written in the form x equals x naught plus a linear combination of the basis for the null space, basis vectors of the null space. Every solution can be written in that form. On top of that, it's even stronger than that. Pick any random list of numbers, real numbers, C1 through Cn. Then maybe to not mix up with that, call this A1 through AN. Then x naught plus A1 times V1 plus A2 times V2 AN times Vn will be a solution. So if you have a solution, you can write it in this form, and by randomly picking any real scalars and putting it in this form, you'll create a solution. So something is a solution if and only if you can write it in this form. An application some of you would have seen already, differential equations, is a nice application of this principle, where we know that if the function y is a solution to a linear ordinary differential equation, then y is equal to yp plus yh, where yp is some, pretty much any particular solution, which is why your differential equation professor, when he was finding y and he ended up having to integrate, he could ignore all the constants of integration because they don't matter. He doesn't have to get a specific one, he can pick any random one. So he just picked the one that has the most convenient constants of integration. So where yp is a particular solution, and yh is the general homogeneous solution. So if you pretend that the equation was equal to 0 and find the solution, you get yh. And in differential equations, you had a theorem that tells you that's what your solutions have to look like. Why? Linear algebra is the reason. The solutions to a linear ordinary differential equation form a vector space. I can translate those solutions to vectors by using the coordinate map. Once I'm there, I can rewrite my differential equation as a matrix equation, and then this theorem tells me that all solutions must look like this. So every solution is expressible in that form, and for any constants C1 through Cn, that will form a solution, and that gives you things like the existence and uniqueness of solutions to a differential equation, where you can know if you find a solution that looks like that, you can stop looking, because every solution has to look like that. There will only be one way to express a solution. And all that comes from just translating to a matrix and finding a column space. You can know all that, which is pretty cool. All you have to do is prove that the solution is a vector space, and you would realize it is, because the solutions are just differentiable equations, differentiable functions that you can solve in a linear fashion. They will obey the 10 rules of vector spaces. Anyway, we will stop there. We'll pick up tomorrow, where we're going to use these guys to expand on our equivalence theorem, and then start to look at linear transformations.